We now have four principles to use when we do proofs with quantifiers. Three are straightforward rules, and the fourth one, universal generalization, is like indirect proof and conditional proof in that it calls for indents. What I want to do here is, rather than go over a review of the rules as such, I want to work through some proofs that will give you a good feel for how they work. Now, some of these are a little bit more complicated than others, and you may find that you need to pause a bit and go back and forth, but that's fine. That's exactly what the purpose of lectures like this is. So let's look at this one. We prove something like this in class. What I'm doing here is first just pointing out that if we have a y as our variable in the conclusion and x is in the premises, it isn't going to matter. And I'm also going to do this in a slightly different way to show another technique for proving universals. How do we prove a universal? Well, one way to prove this universal is to prove, with appropriate indentation and so on, the thing that follows the universal. If we can show that it holds for y, where y is, as we sometimes say, a completely arbitrary object, then we know that it holds in general. So if we could prove appropriately py arrow ry, we would then be able to generalize universally. Now, normally, if you wanted to prove the conditional py arrow ry, you'd do a conditional proof. And we can actually do that here, but there's one little trick that we have to use. And that trick is that we can't get a variable into a proof without indenting. So the variable itself calls for an indent, but we also can't do a conditional proof without indenting, and that's a separate indent. So the way that we take care of this is in two stages. First, we can declare the variable y. This is sort of the technical term. I indented here, and I simply wrote y on line 3, and what I am doing when I do that is saying I'm about to do a subproof in which y is the variable. Later on, I'll have to unindent. I don't bother to write a justification for that. Writing the y like this is simply a way of declaring a variable. Having declared the variable, on the same line, if I like, I could go to a different line, but we can just do it on the same line, I can now make an assumption. I can assume the antecedent of the conditional I want to prove. So this now is an assumption for, in this case, ry. Correct my typo. So I've declared a variable and I've made an assumption. That's two indents. I can now go back to line 1. I can get py arrow qy. That's from 1 by universal instantiation. From 5, I can get qy if I use line 3. From 4, rather, I can get qy if I use 3. So from 3 and 4 by modus ponens, I get qy. Now I can instantiate line 2, and I can get qy arrow ry. That's simply a case of universal instantiation, an unrestricted rule, 2 ui. And now on line 7, I can get what I need to complete this subproof, which is ry. So that comes from 5 and 6. Once again by modus ponens. Having gotten ry, I have completed this conditional proof. So I can draw my scope line, and I can unindent one level back to the point where I declared the variable, and I can conclude if py then ry. So that's 3 through 7. Conditional proof. And then I can universally generalize. I have appropriately indented and appropriately treated as a completely arbitrary object if py then ry. So I can draw another scope line. And I can, on line 9, universally generalize. For all x, or for all y, sorry, for all y, if py then ry. and that comes from 3 through 8 by universal generalization. What I've generalized is line 8, but I had to do that by a process that began on line 3 when I declared the variable. So this is a bit new. You can declare a variable, that's one indent, and then on the same line you can make an assumption for indirect or conditional proof, and everything still works out. Now we're going to go on to talk about quantifier negation. We know from when we talked about interpretations that a principle like this should hold, and in the text what I do is I introduce these as rules first, but here we're going to do it the other way. We're going to show that our rules of proof allow what we already know on grounds of meaning to be proved. So we want to prove that from all x not px we can get not some x px. And this is one of these cases where there's nothing obvious to do except proceed indirectly. If nothing else occurs, simply go indirect. So we're going to assume the opposite of what we want to prove, the denial of what we want to prove, in order to derive a contradiction. And then at this point we can start applying rules that don't have restrictions. We got a choice. We could instantiate line 1 followed by instantiating line 2, or line 2 and then line 1, but we have to do it the right way. When we instantiate line 2, we have to introduce a brand new existential name, and that's why we do it first. From 2 by EI we get this, and then we can go back to 1, and when we do the instantiation here, because the rule universal instantiation is unrestricted, we can make the existential names match, and we can get a contradiction. So 3 and 4 contradict. They contradict because we did it in the right order. If we'd done the universal instantiation first, it wouldn't have worked. On line 5, we simply write the contradiction sign with 3 and 4 as the reference contradicting lines. And this completes our proof except for putting the conclusion on line 6. We can conclude it's not the case that some x are px. Okay? And the justification for that is 2 through 5 indirect proof. Those were relatively straightforward, and we can now treat these as rules that we have. Whenever you have something of this general form, you can convert it into something of this general form. The same for our previous proof. Now we come to something that'll be, did I repeat the same thing here? My apologies if I did. No, here, yeah, now we come to another, we come to another one of a similar sort. It's going to call for similar techniques, but we're proving a slightly different rule. From some x are not p, rather than from all x are not p, we get not all x are p, rather than it's not true that some x are p. Once again, the obvious thing to do is to reason indirectly. So this is an assumption for contradiction. And once again, if we play our cards right, we'll get a contradiction very quickly. We want to do the existential instantiation first so that we can get the existential names to match. We'll get not PE. So you'll see that the proof is in many ways very similar, from 1 by EI. Then we can do our universal instantiation. From line 2, we can get PE, because the rule of universal instantiation is unrestricted. We can write any term we like. And so from 2 by UI, we get PE. Lines 3 and 4 contradict. We have our contradiction, 3 and 4 being the reference lines. We can draw our scope line. And finally, on line 6, we can write the conclusion. So those are pretty straightforward. In both cases, we began with a premise that was a quantifier followed by a negation. We're going to move next to a case that's a little more complicated. Our premise is the denial of a quantified formula, and we want to conclude something that doesn't have a tilde as its first operation. And this will make the proof a little bit more complicated, but it'll work out. So on line 2, we're going to make an assumption because we don't have any rules that we can apply. The obvious assumption is an assumption for indirect proof. So we're going to assume some x, not some x, not px. That's an assumption for contradiction. But now the question is, what do we do? Because we still don't have rules that allow us to take a denied quantifier and swap it around. We need a contradiction. And here, if you think back to what we did with De Morgan cases, you might see what we want to do. If we could only prove for all x px, we'd have a contradiction. Now, how might we prove for all x px? Well, if with appropriate qualifications and indentations we could prove px, use the variable px in a way that doesn't make any special assumptions about it, and prove for all x px, we would have our contradiction. So in other words, we want to prove a universal. We want to prove the universal for all x px. The way to do that in this case will be, first, use this technique that we saw in the very first proof of this lecture. We'll declare the variable. We're going to work with the variable x. And we want now to prove px, so we will do that indirectly. We'll assume not px, assumption for contradiction, and we'll do that because if we get px by universal generalization, we can get for all x px, and we'll have our contradiction. But now we're in the midst of another subproof. We need a contradiction to complete this subproof. Well, where are we going to get that? Look at line 2. It says nothing is such that it's a non-p. But here we have a non-p. If we existentially generalize line 3, we contradict line 2. So 3, existential generalization, gets us what we see on line 4, which contradicts line 2. We could write a contradiction sign. This contradiction is between line 2 and line 4. That means we've completed the subproof that we need to derive px. So on line 6, we can write at the same level of indentation as the x that we declared as our variable. We can write px. It comes from 3 through 5 by indirect proof. Now that we have px, and we've got a proper subproof here in which we introduced the variable correctly and everything else went according to Hoyle, we can do the step of universal generalization. And on line 7, we can write for all x px. Now remember why we did that. We wanted to prove for all x px because it contradicted line 1. So we're still indented here, but we now have a contradiction. Line 1 and line 8 contradict. By the way, let's put the notation for this. This was 3 through 6, universal generalization. We have a contradiction here between 1 and 7. And because we have this contradiction, we can now do our scope line. And on line 9, we can conclude what we originally set out to prove. Sum x not px. That comes from 2 through 8 by indirect proof. Now, look at what we've got here on line 1. We've now shown that from not for all x px, we can get there exists an x such that not px. We've shown that. We're going to use it as a rule. We're developing here our set of quantifier negation rules, and we've now developed 3 out of 4 of them. There's only one left to go, but we can use the ones that we've already developed. So line 1 represents what we can now take to be, in effect, a rule called QN, or quantifier negation. And with that in mind, we come finally to the last case we need to look at. We've got not for some x px. We want to prove for all x not px. Once again, it seems to make sense to proceed indirectly. So this, again, is an assumption for contradiction. And as you might expect, we need to get a contradiction with one of the lines we already got. The obvious candidate is line 1, so we would like somehow to be able to prove sum x px. But notice, go back to the previous proof. We just proved that when you have the denial of a universal, we can turn it into an existential. And on line 2, we have the denial of a universal. If we take what we just learned in the previous proof and we apply it here, we can get, and now we have to be careful about negation signs. We add a negation sign in here, but we can get this from 2 by the rule of quantifier negation that we derived in the previous proof. From here on, it's going to be pretty smooth sailing. So let's first take line 3 and instantiate it. Existential instantiation. Pardon me, we need the double negation at first, but you know what's going to happen. It will drop out quickly enough. So existential instantiation from 3 gets us not PE. Let's go ahead and get rid of the double negation. PE for double negation. Now notice, our original premise says nothing is a P. On line 5, we're saying that E is a P, and so we've clearly implicitly got a contradiction. To make it explicit, all we have to do is existential generalization. We can take line 5, existentially generalize, and now line 1 contradicts line 6. So on line 7, we can write the contradiction symbol. So that's 1 and 6 that contradict. We can draw our scope line. And at this point, we have a completed proof. All we have to do on line 8 is draw the actual conclusion itself for all x not px. So that's 2 through 7. Indirect proof. What we've done then is in these last 4 proofs, we've put together 4 quantifier negation rules that we're now fully entitled to use in any other proof, and we even got a taste of how they work when we got line 3 from line 2 by using one of the forms of quantifier negation we'd already established. Now these proofs are not uniformly simple, they're a bit tricky. You may want to listen to them again, but they give you a lot of insight, I think, into how these quantifier rules work.